All right, this is our start of Chapter 3, Exponential and Logarithmic Functions. We are going to start with Section 1, which is exponential functions and their graphs. So first up is the definition of an exponential function. The exponential function f with a base of a is denoted by f of x equals a to the x power, where a is greater than 0, it's not 1, and x is any real number. So the difference here is that x is in the exponent. So using a calculator, we're going to evaluate each of these functions at the given value. So 2 to the x power, and x is negative 3.1. We go 2, and then we press the caret key here. Notice that that takes you up into an exponent. Type in negative 3.1, press enter. I get 0.116629, blah, blah, blah. So we are going to say that f of negative 3.1 is approximately, right, squiggly equal sign means about, 0.117. We want to go at least 3 decimal places. So let's try 2 to the negative x. So I'll clear that out. 2, little caret, negative, our x is pi this time. Second pi. 2 to the negative pi power is about 0.113. And then 0.6 to the x power if x is 3 halves. So we have 0.6 to the 3 divided by 2 power. I could type it in just like that. I get about 0.465 when I round. So f of 3 halves is about 0.465. All right, so graphs of exponential functions. All exponential functions have a few common characteristics, so let's look at those. If I graph 2 to the x power and 4 to the x power in the same plane. So I'm going to first fill out a table of some coordinates for them. 2 to the negative second power. Remember, a negative exponent drops it to the denominator, becomes 1 over 2 squared, which is 1/4. 2 to the negative first power is 1/2. Anything to the 0 power is 1. 2 to the first power is 2. 2 to the second power is 4. 2 to the third power is 8. So I'm going to graph those real quick. Negative 2, 1/4. Negative 1/2. 0, 1. 1, 2, 2. 4. Oops, I'm sorry, you can't even see those. And 3, 1, 2, 8. All right. This graph looks to me like it is doing something like that. Now let's look at, need a different color, 4 to the x power. All right, for 4 to the x power, 4 to the negative second power is 1 over 4 squared, which is 1/16. 4 to the negative first power is 1/4. 4 to the 0 power is 1. 4 to the first power is 4. 4 squared is 16. 4 cubed is 64. All right, negative 2, we have 1/16, which is right in there. 1/4, 0, 1, 1, 4, 2, 16. I'm already off my graph. All right, it follows that same basic shape. There we go. So notice that both of them share 1 point. The bigger the base, the smaller it gets, but also the bigger it gets, depending on your x values. So let's also look at negative powers. We're going to graph 2 to the negative x and 4 to the negative x in the same plane. So 2 to the negative third power, well, that's going to be the same as, well, negative third. It's 2 to the positive third power, which is 8. 2 to the negative 2 is 2 squared, which is 4. 2 to the negative 1 is 2. 0 is always 1. 2 to the negative first power now is 1/2, and then 1/4. So let's see here. 1, 2, 3, 8, 4, 2, 1/2, 4. And we'll do the same thing with 4 to the negative x power. 4 to the negative 3, 64. Double negative with 2 makes it 16. 4, 1, 1/4, 1/16. So obviously negative 2 I can't fit on my graph, but negative 1 I can. 0, 1, 2. So the only difference between these two graphs and those first two graphs is that they were reflected over the y-axis. So some basic characteristics for us. If y equals a to the x power, the domain is negative infinity to positive infinity. I can plug in any x values I want. The range is 0 to infinity. You'll never get 0, and you'll never get a negative value. The intercept is 0, 1. It'll always cross 0, 1 every single time. It's always increasing. The x-axis is a horizontal asymptote, which means that as x approaches negative infinity, the value of a to the x power approaches 0, and it is continuous. Now, anytime we have a to the negative x power, so, sorry here, a to the positive x power is this one. Anytime we have a negative power, the domain is still negative to positive infinity. The range is still 0 to infinity. The intercept is still 0, 1. The only difference here, it is decreasing. And this one, as x approaches positive infinity, the function approaches 0. And it is still continuous. That is this one that's going down over here. Every single time, no matter what the base is, no matter what x is, that's the same every time. It'll always have the intercept of 0, 1. Then we have the one-to-one property. If a is greater than 0 and not 1, a to the x power equals a to the y power if and only if x equals y. So what this says is if I have 7 to the x power equals 7 to the y power, well, x has to equal y. There's no other way. So that also means if I have 4 to the x equals 4 to the 7th, oh, well, x must be 7 in order for them to be equal. So let's find some examples. We're going to solve 9 equals 3 to the x plus 1 power. Well, I'm going to rewrite 9 as 3 to some power. Well, 9 is 3 squared. And the one-to-one property says that, well, if these two things are equal, those exponents must be equal. So 2 must equal x plus 1. Subtract the 1. So x must be 1 in order to make that happen. 1/2 works very similarly. 1/2 to the x power equals 8. Well, 8 is 2 cubed, which means I could write 1/2 to the negative 3rd power. That'll cube it all, right? 1 over 8, but also flip it, making it 8. So 1/2 to the x power equals 1/2 to the negative 3rd power. Well, x must be negative 3 in order to make that work. So, real quick review. Given a function, how do I write the equation if I shift it vertically? Well, to rewrite my function to shift it vertically, we just add some number on the end. Let's call it, I don't know, z. To shift horizontally, remember, in with the x, we subtract whatever value we want for the shift horizontal. So if I have x, or f of x equals x squared, and I want to shift it 3 right and 5 down, remember that 3 to the right would be x minus 3, squared still, and 5 down would be a minus 5. If I multiply a times f of x, that is a vertical stretch or shrink. And a negative out front, remember that reflects over the x-axis. All right, so these graphs are shifted the same exact way. So if I'm working with f of x equals 3 to the x power, if I put a plus 1 up with the x, that is still a shift. It's in with the x, so it's left and right. It says plus, so it's left 1. h of x is 3 to the x power minus 2. Well, that's outside, so it's a shift up or down. It's minus, so it's down 2. K of x equals negative 3 to the x power. Well, that's a negative outside, which means it's still just a reflection over the x-axis. And 3 to the negative x power, there's a negative, so it's a reflection. And it's in with the x, so it's over the y-axis. Same exact situation as before. Now let's talk about e. E is just a number. You might know some things about it already, but let's talk about it. E is approximately 2.71828 blah, blah, blah. It's kind of like pi. It's an irrational number, not a variable, but it's never ending, so we use e to talk about it. The technical definition of e is the limit as x approaches infinity of 1 plus 1 over x to the x power. That's the technical definition. You don't really need to know that, but there it is. It's also called the Euler number. Yes, that E-U-L-E-R is Euler. So f of x equals e to the x power is called the natural exponential function. E is called the natural base. Okay. The graph of y equals, or f of x equals e to the x power is just like all the others though. It still goes to the 0.01. It is still increasing. All that fun stuff. So let's use a calculator to figure each of these out. To press the e to the x button is a little tricky. If you look, you don't have an e to the x key, but right above ln is a blue e to the x. So I have to press second ln, and then I get e to the power. Now I type in my -2, I get about 0.135. So let's try e to the -1st power. E to the -1, 0.368. E to the 0.25 power, 0.25, 1.284, and e to the -0.3. Oof. 0.741. It works just like all the other numbers. We just have to hit a fancy key to get there. So why do we care about e? If you've ever seen e in an equation before, what was the equation for? There's all sorts of uses, but the most common one is interest. Anytime you have a bank account or take out a loan or anything along those lines, you care about the interest. Simple interest is I equals P times R times T. If you compound annually, that means one time per year. And compounded interest means that you take your principal and any interest you've already earned, and you would get charged interest on all of that. Simple interest just gets charged interest on the principal. The principal is what you originally borrow. So for annually, one time a year, you take your principal times 1 plus r to the t power. If it's compounded k times per year, that means like 5 times per year, 10 times per year, 12 times per year. The formula is a, the new amount, equals p times 1 plus r over k to the kt power. We'll talk about what these variables are in just a moment. And then continuously is a equals p times e to the rt power. Please remember that e is not a variable. But what are those variables? I like to say a is for amount. It's your new amount, new balance. P is your principal. That is the original amount you borrow or put in, deposit, whatever. R is your rate. And your rate has to be a decimal form. If your rate is 5%, you need to use 0.05. T is time. But this is very important because it has to be in years. And K is the number of times compounded per year. So if you're told you get interest monthly, that means it's compounded 12 times a year. Daily would be 365 times a year, that kind of thing. So a total of $9,000 is invested at an annual interest rate of 8.5% compounded annually. Find the balance in 3 years. Let's start by identifying our values. P, our principal. Principal is what we initially borrow. That's $9,000. R is our rate. That's 8.5%, but turned into a decimal, so 0.085. N is the number of times it's compounded per year. If it's compounded annually, that means it's 1 time per year. And T is our time, 3 years, 3. So if I want to find how much the balance will be, I need A equals P, which is 9,000, times 1 plus R over N, which dividing by 1 is just going to be 0.085, to the N, which is 1, times T, which is 3, power. I type this in my calculator. 9,000 times, make sure you put in your parentheses, 5 to the 3rd power. I get remember, we're dealing in money, so 2 decimal places here. $11,495.60. After 3 years. It's a pretty good return on your investment. Well, let's deal with the same situation, but compounded continuously. For continuous compounding, A equals PE to the RT power. Our principal is still 9,000. E to the R is 0.085 still. T is 3 for 3 years. Type this in my calculator. Oops. And I get $11,614.15. I get about $120 more almost. Not too bad. But think about if I left it in there for years and years and years. Continuously compounding interest adds up much more quickly than regular compounded interest. So let's try this. A total of $12,000 is invested at an annual interest rate of 9%. Find the balance after 5 years if interest is compounded quarterly. Find the balance after 5 years if it's compounded continuously. 2 problems here. Let's start with quarterly. All right, for quarterly, our new amount will be our principal, which is $12,000, times 1 plus our rate. Our rate is 9%, which means it's 0.09. Quarterly means that our K equals 4. It's compounded 4. Wait, did I use K or N? What am I doing here? K. Sorry. I called it N last time. My bad. It's K. K is 4. It's 4 times per year. To the KT power. K is 4. T is 5 years. And there we go. We typed that in our calculator. I did not expect you to be able to do that by hand. Now, depending on your operating system on your calculator, you may need to put parentheses around your exponent. The newer ones, if it takes you up into the exponent, you don't need to worry about parentheses around it. But if you have the older operating system where it just does a little caret symbol, then you have to put parentheses around everything that goes in the exponent. So compounded quarterly will have $18,726.11 after 5 years. That is pretty good. But let's see if it's compounded continuously. A equals, my P is still 12,000. My R is 0.09. My T is still 5. I get $18,000 $819.75. Not that much more, right? But it is more. And if you can get more money, you want to. Unless we're talking about borrowing money, in which case you want less because you would have to pay back less. All right, now a different example. Why is the mass of a quantity of a radioactive element whose half-life is 25 years? After t years, the mass is given by this function. Find the initial mass. Well, initial is when time equals 0. If I plug in 0, I have a 0 exponent. Anything to the 0 power is always 1. So that means we get 10 grams. The mass after 80 years, we're going to plug in 80. 10 times 1/2 to the 80 divided by 25 power. I'm just going to type that in my calculator. 10 times 1/2 to the, what is it, 80 divided by 25. 1.088. And there we have it. Make sure if your base is anything besides just a single number, you put it in parentheses. Or if it's a negative, it needs to go in parentheses. All right, fruit flies. The approximate number of fruit flies in experimental population after t hours is given by this equation. What is the initial number of fruit flies? So when t was 0, I have e to the 0 power, which is still 1. So I get 20. How large is the population after 20 hours? That means we are taking q of 20, which is 20 times e to the 0.03 times 20. Calculator again. I get 36.442. Please realize here, though, we are talking about a population of fruit flies. We can't have 0.4 of a fruit fly, so 36 fruit flies. And I should have labeled my 20 as well, right? Fruit flies. All right, that's it for this section. You will have a worksheet to go with it.